On August 21st, 1986, a landslide had occurred around the perimeter of Lake Nyos in northwestern Cameroon. Not long after, more than 1,700 people and 3,500 livestock within a 25-kilometer radius of the lake suddenly collapsed and died. But why? What does a relatively benign event like a small landslide 25 kilometers away have to do with such a tragic phenomenon? To understand this event, and more importantly to prevent it from ever happening again, we need to understand the behavior of ideal gases. So we're ready to start our discussion of gases because we've already discussed intermolecular interactions, and so we know why species exist in the gas phase, right? These are molecular substances in that they are comprised of many molecules, and those molecules have really no significant intermolecular forces. Right? I mean, that's really the key here. If we've got many molecules together in a system, but they're not really interacting with one another, then that means they're remaining separate. And that's precisely what a gas is. It's many molecules separated from each other and not significantly attracting to one another. And in fact, if we assume no intermolecular forces at all, that is the conditions that we say are ideal. In other words, we have a molecular substance that is completely non-interacting and really just existing as independent molecules bouncing around in whatever container that they happen to be in. So, what are the properties of a molecular substance like that? Well, we know gaseous substances expand to fill the available volume of whatever container they happen to be in. And so to describe those samples, we can use a series of experimental observables to do that, one of which would be pressure, often given the symbol P. So pressure is a measure of the force of collisions that individual molecules have on the container that they're contained in. So this pressure is often measured in units of atmospheres, or sometimes pascals, or kilopascals, or torr. There are many units for pressure, but all are really describing the same thing, which is what is the force that a gas exerts outward on its container. Gases also have a volume, of course, that we usually describe with the symbol uppercase V, and generally we talk about the volume of a gas sample in terms of liters, but that doesn't mean we can't talk about it in terms of some cubic distance, like cubic centimeters or cubic meters, or even some SI prefix like milliliters. These are the units we often use to describe volume. There's also temperature, of course. The temperature of a sample of gas is important. We'll learn about how the properties of this gas change with temperature today, but we measure that temperature usually in units of Kelvin or in units of degrees Celsius, which are, of course, related. You've obviously heard of degrees Celsius. This is the common unit system used in weather reporting here in Canada. But Kelvin is the more common SI unit used when describing the temperature of a sample of gas. Kelvin is defined in terms of something called absolute zero, which would be the lowest theoretical temperature possible, which is no motion of your molecules whatsoever. The units of Kelvin are given in uppercase K, and to calculate the amount of Kelvin that you have in your sample, that corresponds to the degrees that you have in Celsius plus 273.15. So this comes from the fact that the Kelvin and Celsius scale are actually the same scale in the sense that a degree Celsius is the same as a degree Kelvin. If you increase your temperature by 1 degree Celsius, you've simultaneously increased your temperature by 1 degree Kelvin. So that unit is essentially the same, but they're on different origins. So if you have a 0 degree Celsius temperature, that corresponds to precisely 273.15 Kelvin. So for every other degree of Celsius you have, you simply add 273.15 to it, and you've got the temperature in units of Kelvin. Now finally, we also have an amount. So how much of the substance do you actually have? And this is often given the symbol lowercase n, and generally we talk about amount in units of moles. So how many moles of gas molecules do you have? And that can help you determine values of the other parameters here as well. So what I'd like to do is explore the relationship between each of these 4 different variables that we use to describe gases. And so that'll help us learn how we can predict their properties in the future. Here's a simulation that will help us think about the properties of gases and how all of these different variables are interrelated. We've got a chamber here and a pump that will allow me to add more gas molecules to this chamber. I'm keeping track of temperature all the time and pressure. And I've got lots of different controls where I can add heat or cool it down, or I can adjust the volume of the cylinder that these gas particles are floating around in, and do all sorts of stuff to try to understand how these ideal gases work. Okay, so remember, the assumption here is that these gas particles are not interacting with one another. And that doesn't mean that they can't collide. You'll notice they're all colliding fairly frequently inside this chamber. But they're not attracted to one another. In other words, as 2 particles pass by one another, if they don't collide, their paths aren't significantly altered. They're not behaving like little magnets, for example, being attracted to their neighbors as they come in close proximity. So this is a gas that's behaving as I would call ideally. All right, so now the first thing I want to demonstrate here is, I think, fairly obvious. It's something called Avogadro's hypothesis, which is essentially pretty simple, and that is that if I add more molecules to this system, it expands. This is the same as blowing up a balloon. More molecules in means that the system will expand so long as I'm keeping it at constant pressure and constant temperature. So this is Avogadro's hypothesis. More molecules in, greater volume. So we say that the amount of gas is proportional to the volume, and vice versa. The volume of a gas sample is proportional to the amount of gas that's inside. Now, I also have the option to grab the side of my container here and squeeze it. Now notice what happens when I do. When I restrict the amount of volume that these molecules are confined to, I am increasing the number of collisions that happen to the side of the container. And that's what pressure is. So take note of my pressure here now hovering around 17 atmospheres. As I squeeze this sample together, these particles are confined to a smaller space and my pressure goes up. In other words, smaller volume, higher pressure, if all other things are held constant. I haven't added any more particles and I haven't changed the temperature. And this makes sense because, as I said, the volume that these particles are confined to is smaller. They will more frequently collide with the sides of the container and generally collide with more force, which is a direct indication of pressure. This is known as Boyle's law, which tells me that the pressure in a gas system is inversely proportional to volume. In other words, if one goes up, the other goes down. And I can do other things. Suppose I were to increase the temperature of this system. Notice what's happening. As I increase the temperature, these particles are moving faster and faster and faster. And as they do that, they're colliding with the sides of the container much more frequently. And as they collide with the sides of the container more frequently and with more force, notice the pressure is now much higher, up to about 96 atmospheres. So this is what happens as I heat this system. This is a demonstration of something called This is a demonstration of the relationship between temperature and pressure in a constant volume system. As the system's volume is held constant, when I heat it up, the pressure goes up. In other words, the temperature is directly proportional to the pressure. Now, what happens with a system like this if I heat it and cool it while maintaining the constant pressure? Now, how would I maintain a constant pressure? What I can do is I can allow the volume here to expand or contract. So if I heat up this system, notice the volume increases. If I cool it down, notice the volume decreases. This is exactly the same phenomenon that happens if you leave a basketball on your front lawn in the late fall and it gets cold overnight. You'll notice that it seems to deflate. But it doesn't. There's the same amount of gas particles on the inside as there was the night before. It's just that the temperature has slowed down the particles on the inside. And likewise, if you heat it back up, it will expand back to its original size. This is a demonstration of Charles' law. Charles' law states that the volume and temperature of an ideal gas are proportional to one another. In other words, if you increase temperature, you increase volume as well, so long as pressure is being held constant. So how can I put all of this together? We see the various laws and hypotheses that we've just discovered by playing around with a gas sample. We know that volume is proportional to, that's what this symbol means, proportional to the amount of gas. Volume is also proportional inversely to pressure. So as pressure goes up, this ratio goes down, which is equal to the volume. And the volume is also proportional to temperature. We've got a lot of different information here. We can put all of this proportionality information together and say that volume is, of course, proportional to the combination of all of these things. N, it's also proportional to T. It's inversely proportional to pressure. These are all simultaneous proportionalities. If the volume is proportional to amount, temperature, and pressure in this way, then we can write it in this way. And there's a neat mathematical trick that I can play here. Whenever I want to change a proportionality symbol to an explicit equal sign, the only thing that I really need to do is add a constant. In other words, a unit conversion constant. So I can say that the volume is explicitly equal to this expression, N times T over P, so long as I include some unit conversion constant. Let's call it the ideal gas constant. I'm going to give it the symbol R, and what that allows me to do is convert this proportionality to an equation. And so now for an ideal gas, I can actually relate the amount, the temperature, and the pressure to the volume and discover how they're all interrelated using nothing more than this ideal gas constant as really just a unit conversion factor. So if I want to use this equation, what I need to do is find this gas constant. Now this gas constant is well known, and it comes in all different kinds of units. The kind of R that you need to use to deal with this equation really just depends on the units that you're working with for the other quantities that you have in this gas law. So the volume, as I said, could be in liters or cubic meters or different sorts of volume units. The temperature is often in Kelvin, but the pressure can be in atmospheres or torrs or millimeters of mercury. There are all different kinds of units. And so the value for R that works in this equation is the one that matches the units of the other quantities. And there are several practice problems that I've assigned for you to experiment with using this relationship in different unit systems. Now, for our purposes, we tend to express this ideal gas law in this concise way. P times V is equal to N times R times T. This is the most common way you'll see the ideal gas law written. And what it allows us to do is actually understand a powerful combination of all of these variables. If you have a sample of gas, by measuring its volume and its pressure, if you know how much you have, you can calculate what the temperature must be for that sample. And vice versa. If you know any three of these four variables, you can definitively predict the fourth. And this has a variety of applications. But most commonly, we apply this ideal gas law to a system that is changing. In other words, it's going from a set of conditions initially to a set of final conditions. Let's see what that looks like. If my conditions are changing, I can write that by using subscripts. So my ideal gas law, where it's normally PV equals nRT, I can write this as P1 V1 equals N1 times R times T1. Of course, R is a constant. It doesn't change depending on the conditions of my system at any point in time. So if initially I have a gas sample that is at a certain pressure P1, a certain volume V1, a certain amount N1, and a certain temperature T1, I can realize that it's so long as this ideal gas sample remains ideal, I can change the conditions and R will of course stay constant. So what would that mean? That would mean I could have P2 and volume 2, and that would be equal to some other amount. And the gas constant remains constant, of course, and I would have a second temperature. So I've got two different versions. Well, not versions, they're really just two of the same thing. I've got a set of initial conditions and a set of final conditions, but they are linked by R. R doesn't change. So what's what we can do? We can do just a bit of algebra and rearrange each of these equations for R. So if I'm interested in what R is equal to, I can divide this side of the equation by N and T and get R by itself. And what that will result in is pressure times volume divided by amount times temperature. And so I'll get that same thing over here on the other side. So now this is with respect to all the second conditions. Now, interestingly, these are both related to the same R. As I said, R doesn't change. It's a constant. So what I can do is equate this set of conditions directly to this set of conditions. And so now I see that they're actually related. In other words, they're bounded to one another. So this is what we call the combined gas law. Combined because we can interrelate two different sets of conditions. Now, practically, when we're interested in applying the combined gas law, it's all about trying to understand a system of gas that is changing. Perhaps its container is expanding, or perhaps you're heating it up or compressing it with a piston. All of these kinds of situations are handled fairly seamlessly with the combined gas law. And it gets easier because what you'll notice if, for example, you have a sample of gas that you're compressing, it's most often true that the amount of that gas has actually remained the same both times. And anything that remains the same can be removed from this combined gas law. But in any case, this combined gas law expands, no pun intended, the application of the gas law to changing conditions, which is useful in a whole bunch of different contexts. And there are several questions assigned to you in your problem set for this week, which will allow you to apply this. I'd like to finish today with gas density. Density is a concept that we can conceptualize quite easily. It's how much stuff we can pack into a particular region of space. More specifically, it's a mass per unit volume. So how much mass can we fit in a particular volume? And we all know gases can be compressed or expanded, and so gases in a container absolutely have a density. And that's an important quantity to think about because it's density that defines buoyancy. Buoyancy is the same principle that allows a boat to float on water. The density of that object is less than the density of the water it's floating in. And it's often surprising to think of gases this way, but gases are also buoyant. So let's see if we can use the ideal gas law to figure out what the gas density should be for an ideal gas species. Now, density is given this symbol. It's a Greek letter called rho. It's sort of a P with a curly end on it. And if density is mass per unit volume, then we can write the density as the mass per volume. Mass we know well from our work with masses, and volume is what we've been working with today. The problem is that mass, though, is not in the ideal gas law. Mass corresponds to amount, though, or at least it can. I know that the number of moles of a particular species, N, is equal to mass over molar mass, right? We've done this sort of calculation a lot. If I've got 5 grams of a substance and I need 10 grams to make a mole, 5 over 10 tells me I have half of a mole. So mass is directly related to amount, as long as I know the molar mass of the particular molecule. Now I want you to think about this carefully. We know that moles is mass over molar mass, and we know that the ideal gas law has volume in it, so we can rewrite the ideal gas law taking this into account. PV is equal to nRT, but now I want to substitute my N for mass over molar mass. There's no reason why I can't do that. That is the same as number of moles. And if I realize that this new version of the ideal gas law is perfectly okay, no different than any other version, I can rearrange it to get mass over volume. So it's going to take a little bit of work, but I have mass here. To get mass over volume, I'm going to have to divide both sides of this equation by volume. I'm also going to want to get rid of molar mass, so I'll have to multiply both sides of this equation by molar mass. And then I'll have to get rid of R times T by dividing by R times T on both sides of the equation. When this is all done, I'll be left with M over V is equal to P, pressure, times M, molar mass, divided by R, the gas constant, times T. Of course, this is density. So the gas density is determined by a handful of factors here. Pressure, I think this makes sense. If we increase the pressure, we increase the density. Of course, if I compress a gas, that sample is now more dense. Temperature is also here. If I increase the temperature of a system, that's the denominator here, which will make the density less. And so increasing temperature, which is increasing the kinetic energy and the motion of my gas molecules, they're going to end up spreading out. We've already seen that with Charles' law. But look at this. We've got molar mass in the expression here. So the molar mass tells me something about the density if I know pressure and temperature. The bigger the molar mass, the more dense my gas substance is. That's a very interesting phenomenon. Carbon dioxide, CO2, has a molar mass of approximately 44 grams per mole, whereas oxygen, O2, has a molar mass of approximately 32 grams per mole. What does that tell us? That tells us that all other things being equal, carbon dioxide will form a more dense gas sample than oxygen. You can see this for yourself in your kitchen by lighting a couple of tea lights, mixing some vinegar and baking soda in a jar, and that mixture of sodium bicarbonate and acetic acid will produce carbon dioxide as a product. That carbon dioxide will stay at the bottom of that jar because it's so dense relative to the air that you're breathing. Now, of course, air is not all oxygen. It's actually mostly nitrogen. But nitrogen is also less dense than carbon dioxide. And what you can do carefully by pouring the jar, you can actually put out all of those candles. You can't see the carbon dioxide with your eyes, but you know it's there because the candles go out. That's because carbon dioxide is a more dense gas. And this brings me to the so-called killer lakes of Cameroon. Lake Nyos is a deep lake that exists in a dormant volcanic crater. The magma at the bottom of the lake constantly leaks CO2 into the water, which gets dissolved in the water of the lake because of the large pressure at the bottom. This is analogous to CO2 dissolved in a can of soda prior to opening it. Disrupting the lake in any way can cause that CO2 to be evolved, and that is exactly what is believed to have happened back in 1986 with a landslide. Millions of tons of carbon dioxide were suddenly evolved from the lake, and due to the fact that the density of carbon dioxide is greater than oxygen, it poured over the land, displacing all of the oxygen and suffocating anything in its path, just like the candles we just saw. Armed with this knowledge, the first permanent degassing tube was installed at Lake Nyos in 2001, with 2 additional pipes installed in 2011. These pipes allow the CO2 in the water to be released into the atmosphere slowly over time so that it doesn't build up, preventing future disasters like the one in 1986.